Morning everyone, I am Sri Charan, AP241-100-11121. Today I am going to talk about sorting for search and why sorting plays a major role in making searches faster and their available applications. Data is everywhere and retrieving information quickly is essential. Sorting is one of the most important steps that helps improve searching efficiency. Before we use fast search algorithms, we often need to sort the data first. But here is the dilemma. Sorting takes order of n log n time. Searching, especially binary search, takes only order of log n time. But binary search only works on sorted data. So the question is, it is worth sorting first if our goal is to search. The answer is yes, because in most general applications, data is sorted once but searched many times. For example, in databases, file systems, and indexing, search operations happen repeatedly. So even though sorting takes some time initially, it greatly reduces the total time spent on the future searches. One of the most important techniques is the efficient sorting of divide and conquer. It works in three simple stages. Divide. Split the problem into small subproblems. Conquer. Solve each smaller part usually by applying the same algorithm recursively. Third one is combine. Merge or combine a solution to form final set of results. Algorithm like merge sort, quick sort, use it to method achieve order of n log n performance. Binder search also uses the same principle, dividing the list into two halves to quickly locate the target element. In this state, the goal, binary search efficiency. The real goal of sorting is enabled to extremely fast searching using binary search. Let's compare. Linear search works on the unsorted data, checks each element one by one. Its time complexity is order of n, slow for large data sets. In binary search, binary search works only on sorted data, cuts the search space in all each data. Its time complexity is order of log n. It is much faster, especially when data size is large. That is why sorting becomes a very important step. Prepares the data so that binary search can work efficiently. Good morning, everyone. My name is Raut Paunse and my registration number is AP2411001142. Today, now I will explain about the match shot. First of all, how the match shot works. Basically, it will be work on the principle of divide and conquer concept. As my friend said, this concept earlier. Now I will explain about these three basic blocks in divide and conquer method. First one is divide method, second one is conquer method, third one is the combine method. First we perform the divide step. Method works by recursively splitting the array into two halves. We keep dividing the array again and again until each subarray contains only one element. Why? Because an array one element is automatically sorted. So breaking the large problem into tiny pieces makes sorting easier later. Now, next comes to the conquer method. Once we have broken the array into individual elements, there is nothing more to sort. A single element is already sorted, right? So at this stage, match sort is basically waiting with these tiny sorted pieces and preparing for the main step. Finally, we come to the last step. That is most important step. That is combination of the divided arrays, subarrays. Now we start matching the sorted subarrays. We take two small sorted arrays and compare their elements and match them into one bigger sorted array. We repeat this matching process again and again. Small sorted pieces to the match and large sorted pieces until the entire array becomes one fully sorted array. In the next slide, we will start coding to the match shot. Now I will explain about how the match function will be work. The match function receives the array and boundary indexes of two sorted subarrays labeled as L1, U1, L2, U2. From L1 to U1 is the first sorted subarray and L2 to U2 is the second sorted subarray. And we are declaring variables I, J, K, and temp. I points to the first subarray, J points to the second subarray, and K points to the temporary array. And here we are creating a temporary array to store the elements matched elements. And we are initialize I to the starting index of the first subarray, and we initialize J to the starting index of second subarray. And we are checking the while condition for the loop continues as long as both subarrays still have elements.
Inside this while loop, we are comparing the current elements of both subarrays. If the element of the first subarray is smaller, store it in temp and increment the I and k. Else store the elements from the second subarray and increment the j and k. This is the main merging logic. After this, we are creating another while loop for if the first subarray still has remaining elements, then store it to the top temporary array and increment the I values and checking the if I less than or equals to u1. Similarly, you can run a loop while j less than or equals to u2 and store the remaining elements of j into the top temporary array. And after that, we are using a for loop from I equals to start index and j equals to 0 and I less than or equals to n and I plus plus j plus plus, which is used to this loop copies the major elements from the temporary array back into original array, starting from L1 to and going up to and index. Each element from the temporary array is placed back into the main array in sorted order. This is the process we are dealing with the merge sort, how it runs, and the time complexity it will take for the whole process is order of n log n, which is the best time complexity compared to the top of quicksort in bad time complexity of a quicksort. And now let's see the coding part for the match chart. We are declaring two functions named as match chart function and match function. Match chart function is used to handle divide step and match function is used to handle combine step. So here we are declaring a void return type which does not return anything. That's why we are returning void, and the function name is match chart. We are for dividing step, and we are taking an array and two numbers. The numbers are L and U. L is for lower index and U is for upper index. Then then it will be checks the condition whether the lower index less than upper index. If the condition is true, the statements inside the if condition will be executed. And also if the condition is true, it means that the subarray has more than one element. So it must be divided further. Here, for this, we are calculating the mid value using the formula mid equals to L plus U by 2. This gives the middle index of array. So we can split into two halves. Next, the match sort m comma L to mid. This stands for match sort again on the left side of the array from L to mid. This is the recursive divide step. And then next line, that is match sort m to mid plus 1 to U. This is the right half of the array from mid plus 1 to U. Again, this continues dividing the array until single elements remain. Later, the merge function combine the left part and right part from L to mid and mid plus 1 to U. It merges them into single sorted segment.
Good morning, everyone. My name is MN and my register number is AP2411001171. Today, I'm going to walk you through one of the most efficient and widely used sorting algorithms in computer science, quicksort. It is called the partitioner swap specialist because of its unique approach to dividing and conquering data. Now, earlier we have covered sorting fundamentals. Now, let's dive deep into the how quicksort achieves order of n log n average case performance through clever partition. Okay, now let's see how the quicksort works. First, we have to pick a pivot. First, we select a pivot element. This could be the first element, last element, and middle element, or even a random element. The choice of pivot is crucial, but because of it determines how well the array gets divided. Think of it as pivot as a dividing line that helps us to organize the data. And next, we have to do partition. We rearrange the array so that all elements are smaller than pivot move to its left, and all the elements larger elements move to its right. The single step organized part of the array and position and the pivot in the final sorted location. Recurrence. Now we have the two unsorted subarrays, one on the left side of the pivot, one on the right. We have to apply the same pick and partition process recursively to each subarray. This divide and conquer approach continue until each subarray is trivially small or 1 0 in use. Now let's see how the partition step works. First, we have to take the last element as pivot, like pivot is equal to a of n, and the p index is equal to start. So we iterate from the start to end -1, comparing each element with the pivot. Whenever we find the element smaller than the pivot, we swap it with the element of p-index and increment the p-index value. And at last, we ensure that the swapping of the p-index and the value. After the loop, we place the pivot at its correct sorted position, like swap a p-index comma a enter. The pivot is now in the final position, elements to its left and smaller, and elements to its right as the larger. We return p-index, which becomes the boundary of our next recursive calls. In the before slide, we have seen how the partition work. Now see the how Quicksort C code implementers works. There are three key functions. First of all, the key function swap function. The utility swap two integers using a temporary variable like temp, and the standard swapping technique like temp is equal to the address of the x, and address of the x is equal to address of the y, then address of the y is equal to temp. They are already covered in the details of the previous set. Core of the algorithm responsible for the organization of elements. Now let's see how the Quicksort function works. The main recursive function that architects the entire sorting process. Base case, if the S greater than or equal to E, the subarray is already sorted. But the recursive case partition, then the recursively sort left and right subarrays. And now we can see the how the S is less than E, then P index is equal to partition of A S comma I. So here the way the partition works, and after that two quicksort will be in order to the completion of the quicksort. Earlier we have saw how the Metsort works and our Quicksort works. Now let's head on and compare the two codes. Like average case, both order is order of analog and both algorithms divide the array into two halves and process all the elements. Worst case, Metsort still order of analog and guaranteed power, but Quicksort order of n square happens when we constantly pick bad pivots like smallest, largest element and already sorted errors. When we compare the space complexity, Metsort needs order of one extra space to match subarrays while quicksort is in place with order of login space for recursion stack. Practical advantage quicksort space complexity efficiently make it preferable for its larger datasets. Like when it comes to stability, Meshsorts maintain relative order of equal elements is stable. Quicksort doesn't guarantee this, it's unstable. However, quicksort speed often outweighs the disadvantage. Like key process, Meshsort divides first and then and measures bottom up. While we come to quicksort, partition first and then recursively sorts the top bottom. So by this we can say that quicksort is generally preferred in practice because of its order of login, space and average of login time with good pivot selection strategies. Thank you.
Hello everyone, my name is Karthik and my registration number is AP2411001140. So I am here to say about binary search. Binary search is an efficient searching technique used only on sorted arrays. Instead of checking element one by one, it repeatedly divides search space in half. So let's check how binary search works. So starting off with two pointers, left and right, marking the start and end of the array. And we should find the middle element next, and we should create a variable what target value is. If it matches, then it will show as element found. If not, if the target is smaller, then it will go to the left half. If the target is larger than the mid value, then it will go to the right half. The process repeats until the element is found or the search space become empty if there is no element in the array. While binary search is efficient, it reduces the problem size by half on every step, so which results in the time complexity of order of login, much faster than linear search for large sorted datasets. So I'm going to the next slide. So now our slide is about real scenario, completely unsorted data. Understanding random distribution. When data is completely unsorted and has no pattern, the first step is to sort it before searching or processing. In such a random dataset, quicksort generally performs better than mergesort because it is slightly slower due to higher overhead. And so let's know why quicksort is faster here. Low constant factors, better cache utilization, very efficient for in-memory data. And performance comparison example. For quicksort, it took almost 45 milliseconds, whereas mergesort takes 60 milliseconds. For random and memory datasets, use quicksort for sorting, followed with binary search for searching. This gives the fastest overall performance. So coming to the next slide, and our present slide is nearly sorted data. The quicksort problem. Quicksort normally performs fast, but if the data is already sorted or almost sorted, something unusual happens. The pivot choice becomes poor, recursion depth increases, and the time complexity degrades to order of m square, which results in very high latency. This is called quicksort pitfall. And we shall talk about the merge sort advantages. Merge sort does not depend on the arrangement of data. Performance stays consistent, always gives order of analog and time complexity. And coming to the performance view of both algorithms, quicksort and merge sort, coming to the quicksort, which has high latency and unpredictable, whereas in merge sort, it is stable and dependable. Coming to the mitigation strategies. To avoid quicksort degradation, use randomized pivot selection or simply prefer merge sort for nearly sorted datasets. So from this we can say that for almost sorted data we should use merge sort instead of quicksort because the pivot is very poor here. And overall takeaways, quicksort is best for random in memory data. Merge sort is best for nearly sorted or very large data. Binary search is fast but requires sorted input. So now my friend will continue with the next topics.
Here, my registration number is CAP 2411001144. I'll continue the presentation by explaining the real world applications of search by sorting. The first example is e-commerce product listing. In modern e-commerce platforms, users expect instant sorting and filtering of thousands of products. When a customer selects an option such as sort by price, low to high, the backend reacts quickly by rearranging the list present in the database of the e-commerce platform. Let's see how. First, if the user picks that sort by price, low to high, then the filter price between 500 to 1500, then the website must arrange thousands of products very quickly. Let's see why the sort is important. Products are sorted like arranging books on a shelf. Once sorted, it becomes easily to apply filters or find a specific item quickly. For example, let me say that numbers are being clumsy, like somewhere random numbers 2, 4. So if you arrange in an order, in an ascending order, then we can use the binary search to quickly uh, select the data which we want, which has the login complexity. And let me tell what is the real world impact by this sorting, searching by sorting. Sorting helps us online stores show results faster, so users don't have to wait. A fast website is it gives a better user experience, and this better user experience gives more sales. And this is how the profit is connected to the our product sorting. And the next real world example is databases. Generally, in databases, we have very large amount of data. Large companies store huge amount of data, sometimes millions of records. For example, a hospital and a bank have many accounts, records, and stubs. So here we come with the concept called external sorting. So when we go with the databases, we will come with words like order by name, order by salary. These are the things we does in the query to take extract data from the database. Sometimes the job is too big to fit into memory at once. So then the external sorting comes to the play. The database sorts the data in small pieces, stores them temporarily, and then merges them together. This is similar like the divide and conquer. The external sort, let's see how the external sort affects the impacts the real world scenario. This allows even giant sets of bigger than RAM. Generally, when the data is bigger than RAM, its accessing will be difficult. So we use external sorting when the data are very bigger than the RAM size. And the things we get efficient due to this external sorting are fast report generation, correct ordering, efficient query execution. The previously mentioned thing ordered by name, ordered by salary, and search by join date. are the things which comes under the query execution. Now let me say with the example, when a bank sorts all transactions of the year, and then we should make a small note that quicksort is inefficient here because it requires random memory access, but disk operations are slow. Merge sort is preferred because it accesses data sequentially, so it will be disk friendly, which is cost effective. It can merge sort sorts large files of data efficiently, so we use the merge sort in this case. And the third real world example is search engines. Generally, in search engines, when you search a word on Google, it needs to find all the pages that contains that word. But Google has millions of web pages and databases to be go on with. So here the concept of indexing comes into the play. Let's see how does it find results so fast. It uses something called, uh, for example, instead of mapping people, we go with the numbers. It maps words, list of pages where the word appears. In the image, we can clearly see that how invert index is used. For example, first the word is given and the pages are sorted accordingly, and the document files are got accordingly. Why sorting is needed in this? To create this index, Google must gather huge amount of words from web page. So sorting them, grouping them, and store them efficiently is one of the important things. This makes searching extremely fast. Result appear in milliseconds. So our Google time, I think it will be very short. So the internal working is this. The internal working is invert index. So invert index needed the index values and the documents with the respective word. So this indexing is done when the data sets are sorted. So here we use the merge sort because merge sort is very useful uh, because the worst case time complexity of merge sort is also order of login. And now let me speak in the real world meaning scenario. Sorting helps search engines organize data so well that they can instantly show search results from billions of documents. It is what I explained. Um, Billions of data sets will be there, documents will be there in the Google database, so we can't index everything into the invert index. So sorting is very important thing in this invert index.
Hello everyone, my name is Rakesh. My registration number is AP2411003170. I am going to tell about total search time order. Sorting takes a time, so it is not always the best choice, especially if we only need to search once. A single linear search is faster in the case because sorting the entire data first would be unnecessary. But if we want to search many times, sorting once and then using a binary search become a much faster overall. After sorting, each search takes only order of big of log n times, which is a much quicker and rapidly scanning the whole list. So sorting is useful when we expert multiple searches on the same data. This is the idea behind the total search time model. Now I'm going to tell about a recommendation. Scenario in case of in-memory array, we use a quick sort to faster average cases and catch locality. For a linked list or a stable needed, we use merge sort, no random access required, and a stable provides huge data like disks. The more efficiently used sort is merge sort and efficiently used real time or a low quick sort is used. At last, now I'm going to conclude this PPT. Sorting and searching works best when we choose the right method for the situation. Quicksort is useful for the fast choice or random in memory address, but MedSort is more reliable when data is already sorted or when we are handling with a large file stored in a disk. Once the data is sorted, binary search gives extremely fast lookup time. The main message is the good sort can be greatly improve search performance. Sorting may cost time and a beginning, but it plays a awful when we search many times. Thank you.